What everyday objects could be considered symbols of the early 21st century? Things you could see on the street and instantly know you're in the 21st century, not the late 20th. In fact, there are quite a few. Smartphones and tablets, electric cars and scooters in all their diversity, drones, and much more. The most interesting thing is that all these innovations became possible thanks to a single invention made at the end of the 20th century, but which fully revealed its potential in the 21st century. I'm talking about lithium-ion batteries, whose inventor, Akira Yoshino, was awarded the Nobel Prize in 2019. Yes, you heard right. In today's video, we'll be discussing lithium-ion batteries. We'll try to understand how they work, what makes them so effective, and why they've become so widespread. We'll also touch on their drawbacks and why thousands of scientists and engineers worldwide are striving to develop something that could eventually replace them. The task of any power source is to create a difference in electrical potential in a circuit. Say, a positive electrical potential at one end of the circuit and a negative one at the other. This difference causes an electric current to flow through the circuit, and the energy of this current can be used to power various devices. In galvanic cells, chemical reactions occurring within the power source create this potential difference, and lithium-ion batteries are no exception. Lithium atoms are characterized by a loosely bound outer electron, as it is the only electron on the atom's outer energy level. Because of this, lithium is highly chemically reactive, meaning it tends to engage in chemical reactions with other compounds. In general terms, a lithium-ion battery is structured as follows. We have two electrodes immersed in an electrolyte. To prevent direct contact between the plates, a porous separator is placed between them. One of the electrodes in a lithium-ion battery, the anode, where a negative potential will form, is made of graphite, a carbon compound in which carbon atoms are arranged in hexagonal crystalline cells, connected to each other and layered one above the other. The other electrode, or cathode, where a positive potential will develop, is a layer of metal oxide, or a mixture of metal oxides. This could be cobalt, nickel, manganese, titanium, or other metals. Here, we'll consider a cathode made of pure cobalt oxide, like those used in early versions of lithium-ion batteries, although today, cobalt is used as sparingly as possible. The cathode and anode are usually made as thin layers of these substances, applied to plates of a well-conductive material, typically copper or aluminum. These plates are also known as current collectors. The space between the electrodes is filled with an electrolyte based on organic solvents containing positively charged lithium ions that have lost their electrons. Their positive charge is balanced by the negative charge of other ions in the electrolyte. When the battery is fully charged, lithium atoms are abundantly embedded in the graphite's crystalline lattice on the anode, a phenomenon in chemistry known as intercalation. In this state, they easily lose their outer valence electrons, turning into positively charged ions, while the electrons remain in a quasi-free state within the lattice. Now let's look at the cathode, where the crystalline lattice of the metal oxide, in our case cobalt oxide, comes into contact with the electrolyte, containing positively charged lithium ions. As mentioned earlier, lithium is a highly reactive metal, so its atoms react with the cobalt oxide, forming a mixed crystalline lattice of lithium cobalt oxide, which has a positive charge. The concentration of positively charged lithium ions in the electrolyte decreases, causing it to acquire a negative charge. This creates an electric field that pulls lithium ions from the anode's crystalline lattice, replenishing their supply in the electrolyte. In this way, lithium ions are effectively transported from the anode to the cathode, resulting in the cathode becoming positively charged and the anode negatively charged due to the remaining lithium electrons. It's worth noting that each successive lithium ion will find it increasingly difficult to migrate from the anode to the cathode, since the electric field of the positively charged cathode repels the positively charged lithium ions, preventing them from reacting, while the negatively charged anode's field attracts the lithium ions, making it harder for them to leave. Thus, the actual potential difference between the cathode and anode will be small, but it will still exist. and the electric field between the electrodes will try to pull the negatively charged electrons from the anode to the cathode. However, the key point is that electrons cannot directly reach the cathode through the electrolyte. If they tried, they would immediately combine with the positively charged lithium ions, turning them into neutral lithium atoms. The electrolyte near the anode would then become negatively charged, preventing the electrons from leaving the anode and compensating for the external field between the cathode and anode. However, if we connect the cathode and anode with a conductor, the electrons will have an alternative path to the cathode, which they will quickly use. Electric current will flow through the conductor, and we can harness the energy of this current. When the electrons reach the cathode, they will combine with the lithium ions, turning them into neutral atoms. As electrons flow from the anode to the cathode, the positive charge on the cathode and the negative charge on the anode will decrease. However, this will be compensated by new lithium ions from the electrolyte reacting with the cathode. Both processes will balance out, and the potential difference between the electrodes, that is, the voltage the lithium-ion cell outputs, will remain roughly constant until all, or nearly all, lithium ions migrate from the anode to the cathode, at which point the battery will be discharged. But it can be recharged by connecting it to an external power source. In this case, the electric field will force the electrons in the lithium cobalt oxide on the cathode to leave their positions in the crystalline lattice and move through the conductor to the anode, which will gradually acquire a negative charge. This creates an electric field that pulls lithium ions from the cathode back to the anode, restoring the state that existed before the discharge began. In other words, during the discharge and charge process of a lithium-ion battery, lithium ions and electrons move from the cathode to the anode in parallel. During discharge, as a result of a chemical reaction between the electrolyte and the cathode, and during charge as a result of the action of an external electric field. That is, both types of charge carriers move synchronously and in the same direction, and not in opposite directions, as in the case of alkaline or salt batteries, but via different paths, and only the energy of the electrons flowing through the conductor is utilized during the battery's operation. This is how the operation of a lithium-ion battery looks in the most general terms, but in practice, there are a huge number of nuances that must be considered. For example, we mentioned earlier that the electrolyte does not allow electrons to pass from the anode to the cathode because electrons bind with lithium ions upon entering it. And this, of course, is great, but it has its negative consequences for the battery's performance. Firstly, in the process, the battery loses part of its charge, which is known as self-discharge. Secondly, the electrolyte contains fewer lithium ions, which it operates on. This is known as electrolyte degradation, leading to the gradual decline of the battery's overall performance. The first lithium-ion batteries were recommended to be fully charged and then fully discharged as quickly as possible, repeating several charge-discharge cycles, which was supposed to significantly extend their lifespan and efficiency. Interestingly, this effect was not anticipated by the developers and was discovered during battery operation, and only later received an explanation. It turns out that during the charging process, chemical reactions involving the graphite anode, lithium, and various electrolyte components occur near the graphite anode, leading to the formation of compounds insoluble in the electrolyte, which form something like a protective barrier on the anode, the so-called solid electrolyte interlayer, SEI. This barrier allows lithium ions to pass through, but remains impermeable to electrons, preventing their direct contact with the electrolyte and all related negative effects. It was precisely to allow this layer to form that the first lithium-ion batteries needed to be fully charged and then discharged, repeating the procedure several times. Today, with the role of SEI in battery operation well understood, this is no longer necessary. Scientists have calculated the ideal parameters for the solid layer, and it is intentionally created at the final stage of battery manufacturing. So modern lithium-ion batteries already have the SEI when you first take them out of the box. Over time, other issues with lithium-ion battery operation have emerged. For example, It turns out that it is contraindicated to completely discharge them or charge them beyond their recommended limits. As we've already discussed, a fully discharged lithium-ion battery is characterized by the fact that all or nearly all the lithium ions have moved from the anode to the cathode, or from the graphite layer to the metal oxide. However, as the metal oxide layer becomes saturated with lithium during discharge, the likelihood of lithium oxide, Li2O, formation increases. Lithium oxide is stable and binds lithium atoms permanently, making it impossible to separate them from the cathode using an electric field later. This leads to a reduction in the concentration of free lithium in the battery and a decrease in its capacity. This process becomes particularly active when the battery charge drops below 5%, and thus discharging the battery below this level is strongly discouraged. If the battery is charged too much, that is, charging continues when almost all the lithium ions have migrated to the graphite cathode, other types of issues can arise. Chemical reactions will start occurring in the electrolyte, it will heat up, and various gases, such as carbon dioxide, will be generated during the reactions. Notably, during this process, heat generation will increase, causing the reactions to intensify further, leading to even more heat release. A kind of chain reaction may occur, which could result in the battery catching fire or even exploding. To avoid these problems, batteries are equipped with a special electronic board that monitors the processes inside the battery and prevents it from operating in unsafe modes. Lithium-ion batteries have revolutionized technology by offering unique, specific energy capacity, meaning they can store record amounts of energy per unit mass. Lead-acid batteries, used in regular cars, have a specific energy capacity of 30 to 40 watt-hours per kilogram. Nickel metal hydride batteries, such as those used in old mobile phones, have a capacity of 60-70 watt-hours per kilogram, and alkaline and salt batteries, 70 to 80 watt-hours per kilogram. By the way, if my dear viewers are interested, in one of our future videos, we could cover the operating principles of other batteries and accumulators used today. If you'd like to see such a video, please let us know in the comments. The specific capacity of lithium-ion batteries can exceed 250 watt-hours per kilogram, largely thanks to the low atomic mass of lithium, which is the primary charge carrier in these batteries. This is why they enable things that were fundamentally impossible with older batteries, and why their emergence has qualitatively transformed our technology. Unfortunately, while lithium-ion batteries are very good, they are not good enough for many reasons. The first drawback of lithium-ion batteries is their safety risk. We've already discussed that they can catch fire and explode when overcharged. Yes, the electronic control unit should prevent this, but what if it fails to do so for some reason? Moreover, the possibility of a short circuit cannot be ruled out. If the plates of the cathode and anode come into direct contact, for example, due to external damage, the battery will rapidly discharge, releasing a significant amount of energy, mostly in the form of heat. As a result, the battery could catch fire or even explode. All batteries, to some extent, are at risk of short circuits, but this issue is particularly acute for lithium-ion batteries. First, due to their high energy density, because the more energy stored in a battery, the more destructive the consequences of its spontaneous release during a short circuit will be. Secondly, the problem is the electrolyte, which, as we've mentioned, is made using flammable organic solvents. The situation is further exacerbated by lithium itself, which has high chemical activity. Manufacturers are well aware of the risks posed by lithium-ion batteries and take serious measures to minimize them. This approach works. A properly made lithium-ion battery is generally safe as long as you don't do anything unusual with it. However, you can never be entirely sure that no defect has crept into the design of a particular product during manufacturing. This is why lithium-ion batteries are classified as hazardous materials. For example, you cannot check devices with these batteries in your airplane luggage. There have been instances where such batteries have caught fire mid-flight, and any airline will do everything possible to prevent this. But the problems with lithium-ion batteries don't end there. One of their significant drawbacks is their high cost compared to other batteries, which is particularly acute considering their limited lifespan. They degrade rather quickly, meaning they lose their ability to retain energy or even fail altogether. There are many reasons why lithium-ion batteries degrade. Dozens, if not hundreds, of scientific articles have been written on various aspects of this process, but here we'll list only the main ones. The first reason is the solid electrolyte interlayer, the same one that, as we mentioned earlier, is essential for preventing battery degradation. However, it also contributes to degradation in the long term. This layer thickens and becomes denser as the battery operates. This leads, firstly, to a reduction in the concentration of free lithium ions, and secondly, it becomes more difficult for the remaining free lithium ions to pass through the layer, increasing the battery's internal resistance. This, in turn, reduces the battery's efficiency and causes it to heat up more during operation, further increasing resistance. Worse still, the solid electrolyte layer may grow unevenly, damaging the graphite layer, which also reduces capacity. As the layer thickens, its permeability may decrease to the point where lithium ions can no longer pass through it, forming deposits of pure metallic lithium outside the layer. These deposits are also known as dendrites. Not only does the metallic lithium in dendrites no longer participate in the battery's operation, reducing its capacity, but worse, dendrites can puncture the separator, causing a short circuit, fire, and explosion, even in a previously functional battery. It's worth noting that dendrite formation is most active when the battery is charged at low temperatures and during fast charging with high voltage. The electrolyte also interacts with the metal of the current collectors and the cathode, gradually dissolving them over time. The dissolved particles contaminate the electrolyte, further reducing its permeability and forming metallic dendrites. Moreover, the gradual dissolution of the current collectors leads to poor contact between them and the cathode and anode, again increasing resistance and operational temperature. Again, these are far from all the reasons leading to the degradation of lithium-ion batteries, but they are the main ones. I think this is enough to understand how a complex set of causes leads to battery degradation, which is why they rarely survive more than 500 to 700 charge and discharge cycles, and near the end of their lifespan, their capacity and other characteristics deteriorate significantly. Continuing with the list of problems associated with lithium-ion batteries, it's important to note that their production requires significant amounts of very specific metals, the Earth's reserves of which, as well as our capacity to extract and process them, are quite limited. And while, for example, cobalt can be replaced by other metals, lithium, which is the heart of lithium-ion batteries, cannot be replaced. Not to mention that producing these metals in sufficient quantities significantly pollutes the environment. And one of the starting points of this whole electric motor story is their environmental friendliness. Lastly, while the energy density of lithium-ion batteries is high, it's still not high enough. 250, 270, or even 300 watt-hours per kilogram is an excellent result for galvanic power sources, but it's still incomparable to the energy density of fuel sources for internal combustion engines. Even 300 watt-hours, as we mentioned, is about 1,000,000 joules per kilogram of battery mass. The specific heat of combustion of gasoline is about 45 million joules per kilogram. Even considering that the efficiency of internal combustion engines rarely exceeds 30%, while electric motors can exceed 80%, the actual specific energy density of hydrocarbon fuel still far exceeds that of lithium-ion batteries, meaning that fuel reserves for an internal combustion engine will weigh many times less than the corresponding battery for an electric motor. And although electric motors themselves surpass internal combustion engines in almost every way, the problem of high mass and cost of power sources negates much of their advantages. This is why so much effort is being put into finding ways to improve battery technology today. These efforts are being made in several directions. Firstly, scientists and engineers are looking for ways to increase battery capacity and reduce charging time. Secondly, they are working on improving battery safety and lifespan. Thirdly, there is active work to reduce production costs and dependence on rare metals. And since this topic, as I mentioned earlier, is one of the most promising areas of scientific research and engineering today, we will touch on new energy storage technologies that are being developed and tested today in our future videos, both in terms of new galvanic cells and fundamentally new technologies based on completely different principles. If you're interested in this topic, be sure to subscribe to the channel and turn on notifications so you don't miss anything. Well, that's all for today, dear friends, and see you next time.